In the last video, we gave an overview of different styles of machine learning, but the advanced AI we're really interested in nowadays involves deep learning, the idea of letting the input data do the programming of a machine so that a machine can reconfigure its code to best complete a task without human intervention, even better than a human creator could have designed it. Deep learning often involves the algorithms of neural networks, which can be thought of as a flexible brain consisting of many neurons, each taking an input and responding with an output. Taking the context of the simplest supervised learning discussed in the last video, such a brain could involve two components. First, a data processor. The fundamental unit here can be thought of as analogous to a neuron. It takes input, does some simple operations, and spits out an output. These operations are all mathematically expressible, for example, taking 2 times the first input, adding 4 times another input, and then giving the output. When many thousands of inputs are evaluated by multiple data processors, whose outputs are the inputs for further processors, we have a model of a brain where the action of one neuron depends on the signals it receives from neurons connected to it. Ultimately, all the data processors can come together to yield one final output result. What we have so far describes any algorithm whatsoever, though. In order to optimize it, we have to figure out how to let the algorithm improve and learn by itself. This involves the second component of machine learning. The second component is a feedback system, some measure of how good the output of a whole network of neurons is. The feedback system, called a cost function, is a measure of how wrong the predicted answer is from the real answer. If we use the example of predicting a price for a house based on its size, the distance to its local facilities, the cost of electricity, and other factors, the cost function could then be the difference between the predicted and actual price. Given this measure of success, we now need to improve the algorithm. Believe it or not, the best way to do this is somewhat like educated guessing. If the current system of neurons performs this well, try again, but with the system of neurons slightly different, so that instead of multiplying one input by 2, we multiply it by 2.1. Does this lead to an answer closer to the correct answer? If so, keep the change and repeat until any changes made only lead to a worse prediction. This sounds like a massive waste of resources, but if you think about it, that's how humans learn to judge unfamiliar situations. By evaluating many similar but slightly different scenarios, we learn what the best scenario looks like. This process of optimization, formalized by calculus, has a fancy name called gradient descent. It's based on the analogy of a mountaineer traversing a 3D landscape of hills and valleys. If we have a two-dimensional plane space of possible neural network arrangements, and the altitude represents how much error the predicted answer has, we're looking for the lowest point in the entire terrain with the lowest error. But we don't have a map of the entire area because that would take too much computation computing the error for every single point. And we can only look a distance of a couple hundred meters around us. So based on what you know, you descend to a lower altitude point and hope that eventually you reach the minimum. Of course, you could get stuck in one valley when there is a much lower valley somewhere else, meaning a more accurate model that is significantly different. This is why the model needs to be trained many times, starting from different locations, and we keep the model that does the best. So AI involves some basic principles: set up a system of neurons with no pre-configured purpose, design a way to evaluate success according to some goal, and try billions of different neuron arrangements until a sufficiently accurate model is found. If this sounds like a powerfully general tool, indeed it is. But if this sounds like a brilliant way to throw resources at a problem with no effort involved in actually understanding the solution, that's partly true as well. Indeed, oftentimes creators of AI don't fully understand how and what an AI is thinking. We've created a model for a neuron that can make a decision, and we've created systems to evaluate how good that decision is, how to structure a whole bunch of neurons together, and how to make this brain very good at doing something. But we don't truly understand the structure of what inputs are related to what outputs and why AI trains itself in that way. This black box situation leads to challenges in the application and regulation of AI, which we'll discuss in the next episode focused on AI policy.